We know that to draw the best Lewis structures, we need to minimize formal charges on as many atoms as possible. However, in some cases, there is no difference in formal charge between possible Lewis structures. The two structures shown below are both correct Lewis structures for formate, CHO2-. Both have the same accumulation of formal charge. In actuality, they are both right. If we look at a charge density map of formate, as we see below, we can see that the negative charge, the red parts, are distributed evenly between the two carbons. The two structures of formate are its resonance structures, structures that can show only part of the reality of the molecule. The true molecule looks like a resonance hybrid, a combination of all possible resonance structures. Resonance structures occur whenever there are two or more valid Lewis structures, but never are the actual molecular structure, whereas the resonance hybrid is the true structure. Notice how the resonance hybrid has partial negative charge that's equally distributed between the two oxygens, just like the electron potential map. The resonance hybrid is always a combination of the resonance structure that is weighted based on their stability. The most stable resonance structures contribute the most. If resonance structures are equally stable, they contribute equally, which is the case here. They are equivalent. Inequivalent structures contribute unequally, but we need to be able to assess the stability of resonance structures to be able to tell this. In order to stabilize a structure, two things can happen. The most important factor for stability is full valence shells. The next most important factor is to have low formal charges. It is essential to remember these two factors because they will help us to understand many of the reactions we encounter in chemistry. Look at the structures of acetyl chloride shown above. Take a moment and assign formal charges to the oxygens and chlorines. Write this down and bring it to class. On the left structure, all the formal charges are 0. On the right structure, oxygen has a -1 formal charge and chlorine has a +1 formal charge. Because the resonance structure on the right has formal charges, it contributes far less to the overall resonance hybrid. However, it still contributes some. The chlorine will have less electron density in this molecule than we see in many others without such resonance structures. Because no atom truly holds a full negative charge in a resonance hybrid, resonance is an incredibly stabilizing factor. The extra electrons are stabilized by delocalization, meaning they spread out to reduce charge in any one place. This is always stabilizing compared to concentrated localized charge. Resonance stabilization is most large when there is significant contribution from more species. This happens when there are many places to localize charge, and when the contributors have similar energy. The more resonance structures, the more stable a molecule is in most cases. Resonance is responsible for an incredible amount of activity. A really fun biological example is the conversion between NADH and NAD+, along with a hydride, H-. Normally it is very difficult to get hydrides. A simple hydride salt like sodium hydride will burn on contact with air or water, for example. However, our bodies are able to generate hydride biologically without side reactions. The trick is that the NAD+ molecule that is left behind by the hydride is incredibly stabilized by resonance structures. The other trick is that the hydride is immediately used for the reaction as well. We are going to use the NAD+ structure to talk about how resonance structures are generated from each other, but first I'll give you some similar examples of electron motion between resonance structures. Moving electrons around, which is represented by curved arrows, is a really important skill that we'll use all year. We'll always draw arrows pointing from the source of electrons, like a lone pair or a bond, and to the new location which the electrons are moving. This can allow us to generate resonance structures without going back to the Lewis structure, and speeds up our understanding of chemistry drastically. Our first example of electrons movement in resonance structures is from a lone pair next to a double bond or a triple bond. Lone pairs can easily move into an adjacent bond, but they can never exceed an octet. If there is an adjacent multiple bond, the electrons from that bond can move out to let others move in. If there is an incomplete valence next to a multiple bond, the electrons from that multiple bond can move in to fill the vacancy. They will leave behind a different vacancy, but usually that vacancy is of a similar energy. Sometimes an incomplete valence, which is almost always a carbocation, a positively charged carbon, will be formed next to an atom with a lone pair. These atoms can form an extra bond to fill the vacancy at the modest cost of formal charge. Lone pairs next to boron also have this characteristic. Anytime double bonds or triple bonds alternate with single bonds, we can generate resonance structures. This is even more important in rings, since the resonance structures will not have formal charges. The example shown is benzene, which has 6 carbon-carbon bonds that are all of bond order 1.5. So back to our example of NAD+. We can easily generate a resonance structure that moves the NH2 electrons into a double bond as we move the double bond electrons onto the oxygen, because we have a lone pair adjacent to a multiple bond. This generates more charge on the molecule, so this is a minor contributor to the resonance hybrid. We can also move electrons from a lone pair adjacent to an incomplete valence, which gives us a structure that is equally charged and therefore equally important. Even more importantly, from this structure, we can move electrons from the nitrogen lone pair to fill the adjacent empty valence with a double bond. This structure is even more contributing than the other two, since it has a full valence on every atom. Finally, because the structure we just drew has alternating double bonds and single bonds all the way around a ring, we can move all the double bonds one position for an equally contributing resonance structure. So there you have it. Resonance structures provide essential stabilization, and we can easily generate resonance structures by movement of electrons rather than redrawing Lewis structures from scratch. And we can tell which ones are most important based on whether they have full valences and whether or not they have substantial formal charges.